In this last section, 6.6, we're going to look at an application with exponential functions, and that would be our exponential growth and decay. We've already worked with exponential growth, and the general formula is this a of t equal to a sub 0 e to the kt. And here k is positive and t is just time. So this is a growth function since the exponent kt is always positive. We're going to have this growth. Now, before we had worked with continuous interest, so remember that was the amount in an account at any time t is equal to the principal that we start with, e to the rt. So this is an example of exponential growth where our value p is at a sub 0 and r, the interest rate, is that constant k. When we have exponential growth, we're just looking at something that increases over time. We also have exponential decay, so that's something that decreases over time. And here notice that it's the same formula, a of t equal to a sub 0 e to the, but it's a negative kt. And because that exponent is negative, that's going to give us that decrease or the decay. When we're looking at a function that decreases over time, an exponential function, it's going to start at some population and it's going to go towards 0 or die out. Oftentimes when we're talking about decay, we also talk about what we call the half-life. And half-life is exactly what it sounds like. It's the amount of time that it takes for the amount to decrease to half of what you started with. So the a sub 0 is the initial amount that we start with. K is just some constant. T is time. So the a of t is just the amount after a certain amount of time. A common problem that we have when we talk about exponential growth is here with the growth of bacteria in example 1. So in example 1, we're looking at some bacteria that grows. Oftentimes this affects food production. So you know that we have perishable items with use by or sell by dates. And that's because they're perishable, and oftentimes the bacteria becomes too high after a certain amount of time, so we can no longer serve that product because it may spoil. So suppose under certain storage conditions, the number of bacteria present, and this would be in millions, in a particular product is given by a of t equal to 300 e to the 0.15 t, where t is in days. So here that 300, it's not 300 bacteria, it's 300 million bacteria because our units are in millions. And with these word problems, you just have to be careful with units. Part A says, how much bacteria are present after 5 days? So all we have to do is replace t in our formula with 5. And if I replace t with 5, I have the amount after 5 days. So a of 5 is equal to 300 e to the 0.15, and t is 5. This is just a calculator problem. When I put this in the calculator, and here we'll just round it to the nearest million. So when I put it in the calculator, I get about 635. So remember, that's in millions. Or in other words, we would have 635,000,000 bacteria. All right. In part B, it says the product cannot be safely eaten after the bacteria count reaches 2 billion. How long will this take? Again, we're just going to put in the 2 billion into our formula. So remember, that's the amount. Of bacteria. So that's our A of T. But remember, we're writing A of T, or the amount, we're writing that in millions. So when we talk about 2 billion, that's going to be 2,000 million. So you may have to adjust units. And we want to find the amount, or the time that the amount reaches 2,000 million. So we're going to replace the 2,000 with A of T in the formula. That should be equal to 300 e to the 0.15 t. So since we're trying to find when, we're trying to find time. I can divide both sides by 300 to get 2,000 over 300 equal to e to the 0.15 t. So my goal here is just to get t equal to some number. And I could see that this will reduce to 20 over 3. At this point, the t is the exponent on the base e. So to get t out from the exponent, I could natural log both sides. So the natural log of 20 over 3 is going to be equal to the natural log of e to the 0.15 t. And once I've done that, by our log properties, this natural log of e is gone. And I simply have natural log of 20 over 3 equal to 0.15 t. And at this point, all I have to do to solve for t is divide both sides by 0.15. And this would be the exact solution. It kind of makes no sense when we're talking about time, and here time is in days. So it's kind of hard for me to see how many days that is. When I put this in a calculator, I get about 12.7, about 13 days. So it's going to be about 13 days for the bacteria to reach an unsafe level. Now, another common use of exponential growth and decay is carbon dating. And carbon dating is actually an example of decay. So carbon dating is a radioactive form of carbon that is found in all living plants and animals. After a plant or animal dies, the radioactive carbon disintegrates or decays. So the amount of carbon-14 that is present after T years is given by this formula here, which would be our A of T equal to A sub 0, e to the negative KT. So it's a decay formula. And here we're told that K is equal to natural log of 2 over 5,700. So we have our K value. And where that K value comes from is that the half-life of carbon-14 is 5,700 years. So let's say that we found a fossil and it contains 30% of the carbon-14 that should be present in it if it were a live specimen. We're going to estimate the age of this fossil to the nearest year. So first of all, let's write out what we know. We know that A of T is equal to A sub 0 e to the negative KT. And we have K, that's given to us. I don't know what my initial amount is though. So it's going to be a negative, and I'm not going to round this in a calculator until the very end. I want to make sure my answer is as accurate as possible. Here's where we're at. So this fossil contains 30% of the amount that should be there. So what that means is it contains 30% of A sub 0, the initial amount, or the amount that should be present if it were a live specimen. If we translate the 30% to a decimal, it would be 0.3 times A sub 0. So that's the amount that this fossil has at this time. That would represent the A of t in the formula. If I substitute 0.3 A of t, or A sub 0, sorry, for the A of t, then this is the equation I would have. 0.3 A sub 0 is equal to A sub 0 e to the negative natural log of 2 over 5,700 times t. So in this equation, if I divide A sub 0 on both sides, I have simplified it a bit so that I have 0.3 equal to e to the negative natural log of 2 over 5,700 t. So I'm trying to find how old this fossil is. I'm trying to find t, where t is in years. So again, I have the same problem I had in the prior problem with the bacteria, is that I'm trying to find t, but t is the exponent. So I'm going to have to natural log both sides to get the natural log of 0.3. And when we natural log on the right-hand side, because of the property, that natural log of e will go away, and I just have negative natural log of 2 over 5,700 times t. Now I can isolate the t by multiplying both sides by the reciprocal, which would be the negative 5,700 over natural log of 2. So my t value is negative 5,700 times natural log of 0.3 over natural log of 2. Again, that is an exact answer, but it pretty much means nothing to me. I can't really tell how many years that is until I put that in a calculator. So we'll go ahead and round to the nearest year. When I put this in a calculator, I get that it's about 990 and round up to 1. So our fossil is about 9,901 years old. So we're going to look at one last example of decay, and this, if you're not familiar with it, is a nuclear accident that happened in Chernobyl in 1986. So this is going to deal with radioactive decay. In 1986, the number 4 reactor at Chernobyl, Ukraine, it went out of control during a test. That led to an explosion and a fire. It demolished the reactor building, and it released large amounts of radiation into the atmosphere. So there were over 100 radioactive elements that were released, but most of these were short-lived. However, about 27 kilograms of cesium-137 was released. And now cesium-137 has a half-life of 30 years. So it lasts for a fairly long time. And this element traveled the farthest and lasted the longest of all the elements that were released. In part A, we want to find an exponential decay model for cesium-137. And when we find that model, we're going to use the fact that the half-life is 30 years so that we can solve for our K value. Well, let's get started. In part A, it is a decay function. So since it is a decay function, I'm going to use that, I don't know where that line came from. I'm going to use that A of t is equal to a sub 0 e to the negative kt. I need to solve for k in this formula. There are some things I do know. I know that the amount that was initially released, and that would be my a sub 0, I know that's 27. So I can substitute 27 for the a sub 0, but I still need k. However, I do know that the half-life, so that's when half of the initial 27 kilograms, I know that that half-life happened after 30 years. So if that is my A of t, half of 27, that would be equal to the initial amount 27 e to the negative k. T is 30 years. So again, in 30 years, when t is 30, we have half our initial amount of 27 kilograms. In this formula, if I divide both sides by 27, that cancels. And again, as we have seen with these other problems, we're going to have to natural log both sides. I think I'm going to write 1/2 as 0.5. It's just easier for me to put in a calculator. So natural log of 0.5 is going to be equal to, now if I natural log the e, it cancels, and I end up with negative 30k. So solving for k, I would just divide both sides by negative 30 to get natural log of 0.5 over negative 30. Now that I've found my k, I can write my complete formula. The amount of cesium at any time is going to be equal to the initial amount, which was 27 kilograms, times e to the negative k, but k here has that negative 30, so those negatives will cancel, and that will be natural log of 0.5 over 30 t. This is the equation that models the amount of cesium in the atmosphere for any time t where t is in years. Let's look at part B. So in part B, it's just asking us to find how much cesium remained in the year 2022, which is the year that we're in. Our formula needs a t value. So we're starting here at 2022, and the year that Chernobyl happened was 1986. So the difference is 36. That's going to be the t value that we're going to put into our formula. So the amount after 36 years of cesium is going to be equal to the amount we started with, which was the 27, e to the natural log of 0.5 over 30. Again, notice I didn't get a decimal approximation for that, even though it is kind of a pain to write that over and over again, because we only want to round our final answer. We don't want to round right now. And so t is 36. I would put that in a calculator. You know what? I think I'm going to, 36 over 30 is 1.2. I think it would be easier if I put 1.2 times the natural log of 0.5 in my calculator. And when I do that, I get approximately, so let's round to the nearest kilogram. 11 point, okay, so I'm going to round up to 12 kilograms. So after 36 years in this current year, the amount of cesium that's still in Chernobyl atmosphere would be 12 kilograms. Let's look at C. In C, it says, when will the cesium-137 decay to 0.1 kilograms? So essentially get to almost zero, and we'll round to the nearest year. So we want the amount to be 0.1 kilograms. So I'm going to replace A of T with 0.1, and that's 27. Oh, that's too close. I'm going to move this down a little bit because I'm going to start squishing into that. Well, now I'm irritated with myself for making a big mess. Okay, so we're 0.1 equal to 27 e to the natural log of 0.5 over 30. And we're solving for t. We're trying to figure out how long it will take for there to be essentially hardly any cesium in the atmosphere. So I could divide both sides by 27, trying to isolate that e so that I can take the natural log on both sides and get that t out from the exponent. Again, natural log on both sides to get the natural log of 0.1 over 27. Natural log on the right means that e will cancel, and I'll have the natural log of 0.5 over 30 t. So at this point, I would just multiply both sides by the reciprocal 30 over natural log of 0.5 to get the t by itself. And this becomes 30 times the natural log of 0.1 over 27 all over the natural log of 0.5. And that is my t value. Again, have no idea what that is as far as years go. When I put that in the calculator, I get 242.3044. So when I round to the nearest year, it would be about 242 years. So quite a while to go till that cesium is almost gone. And that's all I really wanted to cover in this section, just the application of exponential growth and decay. That's it.